Okay, so I just want to talk before we get into today's lesson 11.2. Make sure you know there's a connection between a two-sided test and a confidence interval. So this is the connection. So if you have a 95% confidence interval, that's the same thing as doing a test at the 5% alpha level. If you had a 90% confidence interval, it's the same thing as an alpha level of 10%. They add up to 100%. Do you see how 5% and 95 add to 100? So an 80% confidence interval is the same as a 20% alpha test. So what that means is, even though we just have an interval, we can actually go further. Like normally, if we get, if the interval doesn't capture the null, right? So, oh, it's outside the interval. We have evidence is usually what we say. If it's a two-sided test, we can actually say for a 95% confidence interval where the null is not in the interval, we can actually go further and say, we reject the null. We do have evidence to say that something unusual is going on here. So let's look at an example of one. So at the Hawaii Pineapple Company, the mean weight of pineapples harvested from the field was 31 ounces. They want to try some new watering techniques and so forth. So the next year they changed those to find out. They weigh a random sample of 50 pineapples from this year's crop. So what's the hypothesis here? So null is nothing unusual. All the pineapples are 31 ounces. However, the alternate is we think there's something going on. We think it's going to change, right? There was no direction given. You can check the conditions, but I want to focus on C here, C and D actually. So a 95% confidence interval for the mean weight of pineapples was calculated as 31.2 to 32.6. Based on the interval, what conclusion can you make at the alpha level of 5%? So this is a 95% confidence interval, and the null of 31 is not in the interval. So not only can I say we do have evidence to say we don't think it's 31, we can actually go to the further step of saying because it's a two-sided test there, because this is not equal to, we can say we reject the null, right? We do have evidence to say that the average is not 31. Can we conclude that the different irrigation system caused a change? Well, here's where it gets tricky because correlation doesn't prove causation. Is this a randomized controlled experiment with a random assignment of treatment? It doesn't seem like it because they just kind of like installed this irrigation system in one of the fields. It didn't say it was randomly assigned. We have nothing to compare it to. Instead of being the irrigation system, maybe it was just a better year for crops the next year. Maybe just the weather cooperated. So there could be some other variables or factors. So I don't think we know the answer to that for D. Let's get to today's part of the lesson, which is 11.2. Oops. Okay, so we're talking about difference in proportion. So when you have a test for difference in proportion, the null is always the same. So it's always mu1 minus mu2 equals 0, or just set the means equal to each other would be fine. Because nothing unusual. They're both the same. The new treatment, the old treatment, everything's the same. Conditions are basically the same as they were for the one sample t-test. So no change except you have to do it for both samples. So you have to explicitly say, whatever the sample size is less than 10% for the first group and for the second group there. And same thing for random, same thing for large sample. Here's the painful part. If you have to draw it for one, you have to draw both. So you might have to draw two graphs. That can be painful. Let's just check the conditions here. Has the mean number of hours Americans work in a week changed, like from the 70s to the 2014? Yes, it has. It looks like it. At least we have some evidence. It went from 38.97 to 41.91 hours per week. Evidently, we're working more than 40 hours a week. That's kind of surprising. Does these data give convincing evidence at the alpha 5% level of a difference in the true mean number of work hours? So what would the null be? The null is, we don't think there's any difference. Mu1 minus mu2 is 0. The alternate is there a direction here? So it just says, is there a difference in the true mean number of hours? So that to me means not equal to. So when you do this, it would be, the alternate would be not equal to. So it's a two-sided test. And then you find the parameters there, and you got it. So check the conditions. So does it say something about random sample? I was looking for that. Yeah, responses were from random samples. Less than 10%, so we sampled 764 and 1501, so are both of those numbers less than 10% of the population? In this case, employed Americans, yes, that's true. Our sample size, fortunately, is at least 30, so 764 is greater than or equal to 30, 1501 is greater than or equal to 30. It does, if you want to look at that, it does pass both conditions. That's how you lay it out. So you actually say both of them. You have to specify for both groups in each case. So then you're going to plug into the formula, right? So T, oh, we're not there yet. So we're just checking conditions. So what is the T formula? Well, there's the T formula for you. So write that down in your notes so you have it. This is how you calculate degrees of freedom. So I think it was like the two-prop test as well that we did a couple chapters ago. So it's not just a simple n-1 here. So if you have two different sample sizes, you take the smaller of the sample size and subtract 1. That's a conservative way of doing it. I would say 95% of students on the AP exam use technology. They just want their calculator calculated and they write down it's going to be a crazy decimal degrees of freedom. So it's not even going to be an integer in almost every case. Okay, so explain why the samples give some evidence for the alternate hypothesis. Well, I mean, it went from 38.97 average to 41.91, so we have some evidence. Well, let's actually just calculate the stuff. So you want to calculate T. So you plug in all the values to T, right? And you get 4.88 when you do that. So those were all given to us. That's the stats of the test. Calculate the p-value. So there's two ways to do this. And again, I would personally definitely not do it this way. I would do the test on your calculator. But let's show you what you would do. So let's see, was this a two-sided test? Yeah, we think it was, right? So, but let's just do TCDF here. So menu 6, 5, 5. So lower bound is 4.88. Upper bound is infinity. And degrees of freedom. Ooh. So this is why we should probably do the test first. We could use the conservative degrees of freedom, which would be 764 minus 1, 763. But again, I would prefer, let's just do this in the calculator. So menu 6, 7 is stat test, and this is a 2-sample t-test. We're not going to use data this time, we're going to use stats. X bar is 41.91, hit tab, 14.35, 1501, 38.97, 13.13, 764. Hit tab again, you'll see you have the option there to change that. I think in this case, we were just saying that, is it different? I think, let's see. And then hit tab. Don't change the pooled there. So it should never be pooled when you do this in your calculator. So now we have the data. We can see that the p-value is 0.00001. Degrees of freedom is 1660.58. Wow, so that's a very small p-value. And hopefully you knew that. Like when you see the t-value is 4.88, that's more than 4 standard deviations from the mean, almost 5 standard deviations from the mean. 2 is unusual. So we knew this, we should know this is going to be a very small p-value. We're going to reject almost for sure, right, even without calculating it. So going back to the TCDF, if you did it by hand, I just wanted to mention this. So menu 6, 5, I think it's 5. So 4.88 to infinity. And it was something like 1600.58 or something like that. So that's our p-value, but don't forget you got to multiply it by 2 because we only went in one direction. So then you get the correct p-value that we had a minute ago. So if you use the calculator, you have to worry about multiplying by 2. It just works out. Because our p-value is so small, it's way less than the alpha level, 0.00001. We reject the null. There's convincing evidence. There's a difference in the true mean hours worked by Americans in 1975 and 2014. Okay, I do have a worksheet for this one, but this is just what we're going to put all together, do the whole thing all at once. So does the increasing amount of calcium in our diet reduce blood pressure? Well, I don't know. Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Observational studies don't establish causation, so they did an experiment. Experiments, they picked 21 healthy men who volunteered. They were probably paid. They were randomly assigned to 2 groups. 10 groups received calcium for 12 weeks. The other group did not receive calcium. They had a placebo. Experiment was double-blind. I love that. The response variable is the decrease in this certain type of blood pressure called systolic blood pressure. In millimeters of mercury, an increase appears as a negative number. Now, one of the classes I was teaching had real trouble with this, and actually it's just confusing. So for some reason, I thought negative would be a decrease, but an increase is a negative number. So we think the calcium group's going to decrease in systolic blood pressure, so we want this number to be a positive. So if I have a positive number, minus we know the placebo is going to have much of an effect, minus a zero-ish number, then I should get greater than 0. So I think the key to this problem was getting that alternate is greater than or equal to or greater than 0. The null is nothing's unusual. They're both the same. There's no difference between getting calcium and not getting calcium. It doesn't have an effect, right? That's the null. Nothing is unusual. Define the parameters there. By the way, the reason we discovered it was wrong, the direction of the arrow, is we had a p-value of like 90-something%, and it's just too much. If you check the conditions here, this was random assignment. We don't have to check the less than 10% condition. 10 and 11 is definitely less than 10% of all, healthy men. We don't have to check 10% condition, but we do have to draw the dot plots here. So we do have random samples, random assignment, but you have to draw the dot plots there. So, and don't say they're normal, just say they're not majorly skewed, no outliers, right? That would be fine to say to prove that. So then you plug in the t-value, so plug in all the numbers there. So you have to crunch the numbers. So to just show you how to do that in the calculator, so you would then go to the home screen, add a list and spreadsheet. So call this one calcium, and this one placebo. 7, negative 4, 18, 17, negative 3, negative 5, 1, 10, 11, and negative 2, and negative 1, 12, negative 1, negative 3, 3, 5, 5, 2, negative 11. Okay, so then add a calculator page. We're going to do this in our calculator. So menu 6, test is that, and then to sample t-test. We are going to use data. Choose the name of this one and call it calcium. I might just finish the screencast real quick if that's okay. I'm almost done. Okay, so the alternate was greater than here, so you have to choose greater than. That's probably the toughest part about this particular problem. and you look at all the data, and now we've got the data, and we can use that when we fill in our t-value here. So that's where some of those numbers are coming from, the standard deviation for both of them. You double check your t-value there. You've got it. P-values, degrees of freedom. Because our p-value is 0.0644, way bigger than the alpha level of 5%, we fail to reject. Not have convincing evidence that the blood pressure has decreased for men who take calcium supplements. That's good. That's the end of the screencast.